Hello, in this video we're going to define some more of the probability functions that we operate with when we deal with random variables. Our learning outcomes are thus as follows. By the end of this video I want you to be able to explain what is meant by the term probability mass function, and I want you to be able to explain what is meant by the term probability density function. Before we get onto that though, let's briefly review the one probability function that is introduced thus far. In the video on non-classical probability, we introduced the cumulative probability distribution function and defined it as follows. We said that if each event S in the sample space omega has a value x of S taken from the set of real numbers, script R, then there exists a cumulative probability distribution function that maps each subset of omega that can be formed using this piece of set builder notation to a number from the set of real numbers between 0 and 1. We further said that this function has the following three properties. Its limit as you go to minus infinity is 0, its limit as you go to plus infinity is 1, and it is right continuous. In the video on classical probability, on non-classical probability, we worked out the cumulative probability distribution function for tossing a fair coin looked something like this. We introduced a random variable capital X that took on a value of 0 when a tail came up, and a value of 1 when a head came up. When plotting the cumulative probability distribution function, we then noted that for all x less than 0, no outcomes of the experiments are in the subset formed by taking all outcomes of the experiments with x of s less than 0. The cumulative probability distribution function was thus 0 for all x less than 0. At x equals 0, there was a discontinuous change in the value of the cumulative probability distribution function, as our subset now included the outcome tails. There was then no change in the cumulative probability distribution function until we reached x equals 1, at which point heads as well as tails entered the subset of interest and the cumulative probability distribution function jumped to 1. In parallel to our introduction of the cumulative probability distribution function, we have also discussed the probability mass function, although thus far we have not called it as such. The probability mass function was introduced when we discussed our game of blind man's bluff and ascribed a probability to picking each of the various players. We write the probability mass function for the random variable x using the symbol shown here, small f underscore capital X of x. Furthermore, the probability mass function is equal to the probability that the random variable capital X is equal to small x. For the experiment shown here, this random variable could be one of 6 values, each of which corresponds to one of the mutually exclusive outcomes that we could get from the experiment, i.e. picking Stephen, Conrad, Michael, Carlos, Maeve, or Dawn. Let's now discuss how one calculates the cumulative probability distribution function from the probability mass function. In doing so, we will play a slightly simpler version of the blind man's bluff with only 3 players, 3 mutually exclusive outcomes. The fact that we have 3 outcomes suggests that our random variable can take on one of 3 different values. So we will use the numbers 1 to represent Stephen, 2 to represent Conrad, and 3 to represent Michael. Notice that also the probability mass for x equals 1, we pick Stephen, is equal to P1. The probability mass for x equals 2, we pick Conrad, is equal to P2. And that the probability mass for x equals 3, we pick Michael, is equal to P3. Let's now draw our cumulative probability distribution function. Remember, we construct this function by building a subset of the sample space. The outcome S is a member of this subset if it is a member of the sample space omega, and if some function that takes the outcome as its argument and outputs a number from the set of real numbers is less than or equal to x. No outcomes of our experiment give a value of x that is less than 1. And thus, for all values of x less than 1, our cumulative probability distribution function is 0. When we get to capital X equals 1, there is then a discontinuous change in the cumulative probability. For x equals 1, Stephen is a member of the subset that we pick that have an x less than or equal to 1. The cumulative probability, thus drops to P1, the probability that we pick Stephen. Stephen remains the only member of the subset until x reaches 2. For x equals 2, both Stephen and Conrad are members of the subset. Furthermore, picking Stephen and picking Conrad are two mutually exclusive outcomes from this experiment. We can thus calculate the probability that capital X is less than or equal to 2 by adding together the probability that you pick Stephen, P1, and the probability that you pick Conrad, P2. Between 2 and 3, the value of the cumulative probability is once again constant, as no new outcomes from the sample space enter the subset. However, all three outcomes, Stephen, Conrad, and Michael, have x values less than or equal to 3, and thus at x equals 3, the cumulative probability distribution function jumps to 1, suggesting that generating a random variable less than or equal to 3 is assured. Hopefully, by doing this little experiment, I will have convinced you that when our random variable takes on integer values, the probability mass function gives us the probability of generating each of the possible values the random variable can take. In addition, because for each capital X value corresponds to a distinct and mutually exclusive outcome of our experiment, we can calculate the cumulative probability distribution function from the probability mass function using the summation shown here. Last but not least, if we add together the probability masses for all the possible values of capital X that the random variable can take, we get a value of 1. When this is the case, we say that the probability distribution is normalized. Let's now turn to a slightly different scenario. Let's suppose that the outcome from our experiment is a number between 0 and 1. There are an infinite number of numbers between 0 and 1, so we cannot construct a probability mass as we did in our previous example with the game of Blindman's Bluff. We can, however, draw a cumulative probability distribution function immediately instead. We know that the outcome from our experiment is between 0 and 1. Hence, for all values of x less than 0, there are no outcomes of the experiment in the set formed by taking all outcomes with the random variable less than or equal to 0. The value of the cumulative probability distribution function must thus be 0 for all values of x less than 0. We can apply a similar logic for values of x greater than 1. We know that the outcome from our experiment will always be between 0 and 1. Hence, for any value of x greater than 1, the cumulative probability must be 1, as all possible outcomes of the experiment will give a random variable less than or equal to 1. We can then fill in the space between these two extremes by using the fact that all outcomes between 0 and 1 are equally likely. This implies that the probability of generating a value less than x will increase linearly as x is increased from 0 to 1. Putting this in a slightly different way, as you increase of x, the proportion of outcomes with random variable values less than x increases linearly. Hence, if all of these outcomes are equally likely, the cumulative probability, the probability of generating a random variable with x less than or equal to x, should also increase linearly. In the previous video on non-classical probability, we discussed the following limit and how this must be obeyed at all points along a cumulative probability distribution function. We visualized what this meant by drawing a blue circle at x as shown here and a green circle at x plus epsilon, and then showed that as we decreased epsilon, the green circle moved back along the curve until it overlaid the blue circle for epsilon equals 0. In this way, we showed that the limit shown was satisfied by the cumulative probability distribution function. While discussing this limit, we also talked briefly about the limit shown here, where instead of having x plus epsilon, we have x minus epsilon. In the previous video, we showed that this limit did not hold for the cumulative probability distribution function that we obtained for tossing a fair coin. Here, though, this limit does hold. Once again, we place our blue circle at x and our green circle at x minus epsilon. and show that when epsilon is decreased to 0, that the green circle overlays the blue circle. The fact that both the x plus epsilon and x minus epsilon limits are equal to f of x is important, and it implies that our cumulative probability distribution function is continuous and thus differentiable. When neither of these limits or only one of these limits hold, the function cannot be differentiated. An interesting exercise is thus to draw a graph of the derivative of the cumulative probability distribution function as a function of x. As an exercise, pause the video and see if you can draw this curve. Your curve should look something like this. For x less than 0, the cumulative probability distribution function is a horizontal line, and thus the gradient is thus 0. Between 0 and 1, the function increases linearly, and the gradient is thus constant. In fact, the gradient is equal to 1 as x changes from 0 to 1 and y also changes from 0 to 1. For x greater than 1, the curve is once again horizontal and our derivative is thus 0 once more. Now remember that integration, calculating the area under a curve, is the opposite of differentiation, finding the gradient of a tangent to a curve. We can thus take the derivative of the cumulative probability distribution function that we have just drawn and recover the original cumulative probability by finding the area underneath the horizontal line. This process is illustrated in the following movie. The area of the shaded region underneath the lower curve corresponds to the value of the blue dot shown on the upper graph. When we have a cumulative probability distribution function like we've just seen, which has a derivative by virtue of having that the limit of f of x plus epsilon is equal to the limit of f of x minus epsilon as epsilon tends to 0, we call the derivative of the cumulative probability distribution function the probability density function. This is given the symbol shown here. It is sometimes written like this, although saying that the probability density is equal to the probability that the random variable has a particular value is not quite strictly correct, hence the inverted commas. There is good reason for writing this though. As we have just seen, we can recover the cumulative probability distribution function from the probability density function, the derivative of the cumulative probability distribution function, by taking the following integral. This looks rather similar to the way that we recovered the cumulative probability function from a probability mass function when we had a random variable that could only take on discrete integer values. The equation for doing this is shown here. If you remember, for these discrete random variables, we also had the sum of all the elements of the probability mass function was equal to 1. We have a similar condition for the probability density. The integral of the probability density over all space is equal to 1. We thus arrive at a reasonable rule of thumb. When you move from a random variable that can take on only discrete integer values to a random variable that can take on real number values, all the summation signs that you had turn into integral signs, and probability mass functions change into probability density functions. This holds for the normalization conditions, the way that you convert from a probability mass/density function to a cumulative probability distribution function, and as we will see in subsequent videos, the way that we calculate expectation values. For now though, let me finish and summarize by reminding you of the two probability functions we have learnt about in this video. The first of these is the probability mass function, which can be used when our random variable takes on discrete integer values. The probability mass function tells you that the probability that the random variable capital X is equal to the number small x. The second probability function we have introduced is the probability density function. This is equal to the derivative of the cumulative probability distribution function, and it can only be calculated when the random variable can take on a continuum of real number values. I hope you've been able to understand these concepts from this video. If not though, watch it again and see if you can get them on the second time through. Thank you.